Ever wonder how your GPS just knows the fastest route, dodging all the traffic? Or how data zips across the entire internet to land on your screen in like milliseconds? Well, it all comes down to solving one huge problem. What's the absolute shortest path? So let's get into the elegant, powerful, and honestly, surprisingly simple algorithm that makes our modern world tick.
Our story actually starts with a pretty simple question, way back in the Netherlands in the 1950s. A young computer scientist needed to show off a new computer to people who'd, never even seen one before. So he picked a problem that anyone could understand, but that was actually really tricky to solve. Find the shortest possible route between two cities on a map.
And the solution came from this guy, Edsger Dijkstra. But the most incredible part of this whole thing is what he said right there. 20 minutes. Get this, he was tired from a shopping trip with his fiancée, sat down for a coffee, and just came up with one of the most important algorithms in all of computer science in his head?
That's right, a 20-minute coffee break. And this isn't just a fun piece of trivia, it's actually central to understanding why this algorithm is so powerful. It's a story about a human brain finding a beautiful, elegant solution to a really complex problem, not by throwing computing power at it, but with just pure, simple, clear thinking.
Okay, so if you look at the timeline, you can see how it all played out. 1956, he has the idea. And the key detail, which he talked about later, is that he designed it entirely in his head. No pencil, no paper. He said this basically forced him to avoid all avoidable complexities. Later that year, it got put to work mapping the 64 biggest cities in the Netherlands. But here's the wild part. It wasn't actually published until 1959, a 3-year gap for an idea that, today, pretty much runs our world.
So we've got the who and the why. Now for the really fun part, the how. How does this thing actually think? We're going to walk through it, and I promise you'll see that its genius is all in its methodical, step-by-step logic.
Okay, first things first. We have to translate a real map into a language a computer gets. And for that, we use something called graph theory. Just think of the whole map as a graph. Every city or intersection, that's a vertex or a node. And the roads connecting them are edges. And each edge gets a weight. That can be the distance, the time it takes to travel, whatever you want it to be. So here's the play-by-play of how it works. Step 1. You tell it where you're starting. It sets that distance to 0 and every other point to infinity, which is just a fancy way of saying we have no idea how far it is yet. Step 2. It looks at all the spots it hasn't visited and picks the one with the shortest known distance. Step 3. From that spot, it looks at all of its immediate neighbors. Step 4. It calculates if going through the current spot creates a shortcut to any of those neighbors. If it does, it updates the distance. And finally, step 5. It marks the current spot as visited, and then just repeats the whole process, always expanding from the closest point until it gets to where you're going.
Now, the secret sauce here is that Dijkstra's algorithm is greedy. That just means that every single step, it makes what looks like the best choice right in that moment. It always jumps to the next closest, unvisited spot. It doesn't have to second-guess itself or go backwards, and this relentless forward-moving strategy is exactly what guarantees it'll find the absolute shortest path super efficiently. But that laser focus is both its biggest strength and its one real limitation.
I mean, it sounds perfect, right? Guaranteed shortest path, found super fast. But, like any tool, it's built for a specific job. So is it always the one you should reach for?
Its one main kryptonite is something called negative weights. Just imagine a route that, for some weird reason, pays you to take it. It has a negative cost. Dijkstra's algorithm would get totally confused and stuck in a loop. For crazy scenarios like that, we use a different tool, like the Bellman-Ford algorithm. It's a bit slower, yeah, but it's built to handle those weird negative weight problems you might see in things like finance.
But let's be real. For the vast majority of problems in our world, from road networks to the internet, Dijkstra's is king. And its impact, oh man, it goes so much further than just figuring out how to get from Rotterdam to Groningen.
Just think about your day. When Google Maps finds you the quickest way to the store, that's Dijkstra. The way data packets find the most efficient path across the internet to bring you this explainer, that's powered by protocols that use Dijkstra. Figuring out your degrees of separation from a celebrity on a social network, yep, that's Dijkstra too. It's in video games helping characters find their way, it's in robotics, it's even used to solve puzzles like a Rubik's Cube. It is everywhere. When you really step back and look at it, it's just mind-blowing. This one beautiful, clean idea, cooked up in 20 minutes, laid the foundation for solving a massive number of problems.
It is the perfect example of how a simple, elegant piece of logic can have a truly world-changing impact. And that brings us right back to where we started. That simplicity wasn't an accident, it was the whole point. By forcing himself to design it purely in his mind, Dijkstra had to find the cleanest, most direct solution possible. The elegance of his process led directly to the elegance of the final algorithm.
It really makes you wonder, doesn't it? As we stare down all these incredibly complex challenges in the world, maybe the answers aren't always more complicated systems. Maybe some of our biggest problems are just sitting there, waiting for someone to sit down, clear their mind, and find that simple, beautiful 20-minute idea.